Now, bone cells. Bone-forming cells are osteoblasts. And like fibroblasts and chondroblasts, their job in the case of bone is to secrete bone extracellular matrix. Osteoblasts are derived from osteoprogenitor cells, which are formed again from multipotent mesenchymal stem cells, the same cells that give rise to all resident or support cells that form connective tissue. Osteoprogenitor cells may be carried into pre-existing cartilage in the connective tissue from surrounding blood by way of blood vessels that grow into cartilage during embryogenesis or from connective tissue residing in the bone marrow spaces during subsequent bone growth and remodeling. And as we'll see, there are fundamentally two different forms of bone. A solid mass of bone forms compact bone, whereas spongy or cancellous bone consists of a network of spicules or trabeculae that are separated by spaces containing hematopoietic cells in the bone marrow. Osteoblasts are specialized to synthesize the components of osteoid, and the major collagen component of osteoid is type 1, along with glycosaminoglycans. The unique structure of the osteoid promotes the formation of a crystalline structure known as hydroxyapatite. Osteoblasts adhere to a surface, such as cartilage or a pre-existing osteoid, and continue to secrete new osteoid in a polarized manner only onto the attached surface, leading to appositional growth of bone. Picture on the next slide shows a haversian canal that's lined by the squamous osteoprogenitor cells that tend to be flattened, probably those at two of the arrowheads. Osteoblasts tend to be more cuboidal. Both cell types are highly basophilic. And inside the haversian canal are also blood vessels, nerves, and so on. In compact bone, as shown here, we can see that compact bone consists of a number of individual haversian canals, and surrounding those haversian canals are circumferential lamellae that basically contain lacunae with osteocytes in them. So the osteocytes are shown basically at the arrowheads, and the osteocyte lacunae are all interconnected by small canaliculi. And in those canaliculi are processes of the osteocytes that are all linked together by way of gap junctions. Next, in addition to having osteoblasts, which are bone-forming cells, bone also contains osteoclasts. These osteoclasts are responsible for the breakdown and the absorption of bone matrix with the subsequent release of calcium into the blood. Osteoclasts are derived from monocytes. They have a blood monocyte lineage and ultimately come from hematopoietic stem cells that are in the bone marrow. During early embryogenesis or bone formation or remodeling, where there is no adjacent marrow, the precursor cells that give rise to osteoclasts are recruited from circulating blood cells, and later, basically when the marrow cavity appears, they will be derived directly from hematopoietic cells in the bone marrow. Picture on the next slide shows a classic view of a multinucleated osteoclast, because it's formed by a fusion of a number of monocytes that give rise to its multinucleated appearance. These cells are easy to distinguish from an osteoblast, which is typically an osteocyte. An osteoblast is typically a cuboidal basophilic staining cell, whereas the osteoclast is much larger, multinucleated, and it's much more eosinophilic. Now, there are two different mechanisms fundamentally of bone formation. The first of them is intramembranous bone formation, where primitive mesenchyme can give rise directly to bone without utilizing a cartilage precursor. Intramembranous bone formation takes place in the formation of the flat bones of the skull during embryogenesis and in the growth and thickness of dense cortical bone on the surface of bones. During embryogenesis, flat bones begin as small collections of condensed mesenchymal cells that are induced to become osteoblasts. As the collections grow, they fuse into interconnected cords, which will form trabeculae, which will be surrounded with intervening mesenchyme. Ultimately, intramembranous bone will give rise to primary spongy bone and has a randomly arranged array of cartilaginous fibers in its matrix. Picture on the next slide shows a intramembranous bone formation consisting of newly formed spicules at the tips of the arrows, And you can see that these spicules contain osteocytes already embedded in their lacunae at the arrowheads, and they're surrounded again by the mesenchyme of primary spongy bone in the adjacent marrow-like cavities. In contrast, endochondral bone formation requires the existence of a pre-existing plate of hyaline cartilage. And endochondral bone formation is classically located in the long bones of both extremities, in the vertebrae, and in the bones of the pelvis. As we said, endochondral bone formation starts by utilizing, or starts as a hyaline cartilaginous template, which is formed from chondroblasts and chondrocytes by way of differentiation from chondroid progenitor cells that we've seen already that are derived from mesenchyme. Picture on the next slide shows endochondral bone formation and the stages that are involved in it. So on the left side of this picture is what we refer to as the reserve zone of resting chondrocytes and chondroblasts in existing lacunae. In the middle at the tip of the arrows is the zone of proliferation, and on the right basically is the zone of hypertrophy where the chondrocytes ultimately are undergoing programmed cell death and are invaded by osteoprogenitor cells that will form bone components of matrix. So here's the sequence. The epiphyseal growth plate shows the following sequence for bone growth from early fetal development up to puberty. The reserve zone, as we said, which was shown on the left side of the previous slide, consists of chondrocytes in their lacunae at the epiphyseal end of the growth plate. The proliferating zone is deep to, or is in the middle of, the reserve zone and the zone of hypertrophy, and it consists of proliferating chondrocytes that form clones arranged or aligned in columns parallel to the long axis of the bone. The zone of hypertrophy consists of chondrocytes deep to the proliferating zone that are gradually undergoing hypertrophy by becoming larger, producing type 10 collagen and growth factors. And it is those hypertrophic chondrocytes that then undergo programmed cell death or apoptosis. Mature bone basically consists of a series of Haversian systems, and mature bone undergoes a constant process of remodeling as generated by the activity of osteoclasts and osteoblasts. So in this histologic image, we see that a Haversian canal is surrounded by newly formed circumferential lamellae at the arrows, and interspersed between those Haversian systems are remnants of remodeled Haversian systems that form interstitial or older bone lamellae.